Thank you. Okay, so today I'm going to talk about onshore and offshore LiDAR, and a few of you, I apologize, may have seen some of the slides on the onshore. I'm going to go through those pretty quick because I want to give you a peek at this new Bathymetric system that I'm talking about. But first, for those that aren't familiar with LiDAR, a few LiDAR principles, getting into some little historic digital elevation models before and after, a little bit about what we can get from traditional topographic LiDAR from an earth science point of view, and then moving into this topobathy business. Okay, this just is an example showing you where different LiDAR sites have been flown. I feel bad that it's circa 2004 because we do have many more areas covered now, but for those not familiar, LiDAR is an acronym for light detection and ranging, and essentially what we're doing is firing a laser pulse, a laser ranging system from the aircraft, measuring the two-way travel time to get the range. We have a survey-grade GPS and an inertial measurement unit to measure the attitude of the aircraft, and we basically are positioning point clouds. This particular sensor scans in a back and forth pattern, and as the aircraft advances, we're scanning in a sawtooth pattern. And that's about it. So it gives you a detailed point cloud from an aircraft. This shows us the track around an area just south of New Brunswick. This is the Musquash Marine Protected Area. Here's an example of a cross-section along the coast of the point cloud, and we can see vegetation and the ground. We use software to go through and essentially classify the ground beneath, and that's the real power to the geologist, is the ability to see through the trees, if you will, and see the ground. This shows us the LiDAR swaths for that same area. So for every line, we have a swath where the system surveyed them. And for ground areas, we normally try to fly at about a 50% overlap to compensate for shadows and so on. Okay, we get a point cloud. To make use of it in a GIS system, we basically go through a process moving from points through some sort of interpolation process, say a triangular or regular network, into a grid. And just to give you an idea, a lot of the, seems like this laser is kind of giving up the ghost. The provincial, we have a 20-meter elevation model derived from photogrammetry. With LiDAR, we can routinely get down to 1 to 2 meters, so a real jump in terms of resolution and detail we can see. This is something from my master's degree. This was a DEM I was proud as heck of back in 1987, where basically we were looking at 1 to 250,000 contours to map out the Cobequid-Chedabucto Fault. So it just is a bit of a history from where we were then to, and now we'll look at some LiDAR from the valley. Many of you have probably seen this. This was stuff surveyed in the summer, so maximum leaf canopy. These show all of the points that made it to the ground. So we can see the cleared areas. It's basically painting the landscape every meter or so. And in the forest, not as many points get to the ground, but still a significant amount. So this shows us all of the LiDAR points. So we call this a digital surface model, colored by elevation. So the Bay of Fundy, moving up to the top of the North Mountain. This is just by the Annapolis Valley, down into the valley again. And we can see the road, we can see a little swamp, a little bog in there, and some of the gross features. Here's the real strength of it from a geoscience point of view. We can strip away the vegetation, and now we can see individual flows of the North Mountain basalt. The big contact ridge here between the upper flow unit and the middle flow unit, a little more subtle contact with the lower flow unit. And Dan Contact and I have published maps for DNR Open House here using LiDAR as to assist in Dan's mapping. So those are all available. And there's just an example of what we have from the 20-meter photogrammetric DEM. So quite a difference in terms of the level of detail and all kinds of application in terms of hydrology and where water will flow. Another example, karst topography up here around the Oxford area. Here we see the digital surface model. The ellipse is going to highlight when we remove the trees. We can very clearly see this very pucked pattern, and this is basically where we see karst topography. So from a geohazard, from looking for limestone-hosted mineral deposits and so forth, the LiDAR will quickly allow you to identify things like karst topography. Just a couple more on the North Mountain. So we have the upper flow unit, outcrops along the coast, very resistant, hard, thick unit. Then we have the middle flow unit, a variety of thinner flows, very vesicular, contains the stilbite, our provincial mineral. And then lastly, we have the lower flow unit, again, a thick, massive columnar basalt. And we can go through and make use of GIS and the topography to help us map out the planes of where these contacts come through. This is, I won't go into it a lot, but basically I did this exercise to essentially assist where we had glacial till cover. Now, on the point of glacial till cover, the LiDAR doesn't see through the glacial till, not like ground-penetrating radar. So, but if you can't beat them, you got to join them. So here's an example where we strip away the vegetation, and there's a couple of interesting features. We can see these, this large esker system, and we can also see how it's been truncated by the last high sea stand after the area has been deglaciated. So fantastic evidence to mark that higher sea level. And we can then go about making use of the bedrock plane and so forth to calculate the depth of that sediment. So very good for evaluating aggregate resource volumes and so on. This is just a big CAME system near Margarettsville. Very similar type of process I'm going through. Okay, on to what I really wanted to talk about today. Now, when we're mapping, and I'm a mapping guy, we have Topo LiDAR that I've just been showing you, and this is the North Mountain. Of course, we have multi-beam bathymetry for the deeper water. And we often have this white ribbon gap where it's very tough to map the near shore. Land techniques don't work. A multi-beam ship, the efficiency drops down because you are surveying a very narrow swath. And of course, you have navigation safety issues on the boat. So this is where this new technology of bathymetric LiDAR can fill in that gap and essentially fix the white ribbon. So here's St. Mary's Bay and PEI. Here's an example after a bathymetric survey. So we now have continuous elevation from the land, and we didn't penetrate into the deeper part of the channel here, but almost continuous, and that could be easily picked up with a boat and an echo sounder. Now, what I'm going to do is show you some results from a study. We just surveyed an area in September, and I'm going to show you some areas around a place called Cape John, Nova Scotia. Here's Tatamagouche, so we're in the Cumberland Basin still. And the principle behind this, the traditional topographic LiDAR uses a near-infrared pulse to come down and reflect off the surface. It doesn't penetrate the water column. The bathymetric LiDAR uses an additional green laser, 532 nanometers. And the principle here is that the red laser pulse will detect the water surface, the green laser pulse will refract, go through the water column, and ideally reflect back to from the seabed back to the surface. And this just shows you the waveform of the transmitted pulse and when we finally get a reflection from the seabed. I feel like a LiDAR here having to pulse this thing. Here's an example. It's just, I'm not going to read all these specs, but it's a topo laser that's firing at 500,000 shots per second. The bathymetric laser has to build a little more power before it shoots its pulse, so it's only firing at about 35 kilohertz. We actually bought the system from Sweden, had a little bet on who won the men's hockey title there at the Olympics, so he had to wear that around the office for a week, the director of that company. Thank you. This is the actual laser head. In addition, it has a 50 megapixel camera on board that images both true color and a near infrared signal. So if you're looking for, say, stress vegetation for things related to mining or mineral deposits, this near infrared band in the camera would really help with that. And this is the control rack. There it is with the cover on board. See, I don't just sit in the office. I actually went up and operated. Thank God I had this young fellow to tell me exactly what button to push, but there we went out on a survey. This is basically what you see that tells you you're coming online and what's controlling the camera. And then I'll zoom in on this. Basically, this is showing you a quick snapshot, and this would be the pulse when it reflects off the water, and this secondary pulse would be the reflected signal back from the water. So you can quickly tell if you're getting good returns through the water column or not. And I think I have a slide coming up that shows Upper Bay of Fundy, where the water's extremely murky. It's not going to work. You need to have fairly clear water in order for this technology to work. So we make use, and a general rule of thumb, this is a 20 centimeter black and white disc called a Secchi disc, and this sensor will basically do 1.5 Secchi disc depth. So if we lower it in this kind of murky water and we lose it at 1 meter, then we can probably expect to only get penetration 1.5 meters. But if we go down, say 3 meters, then we'll be in the 7 to 8 meter range. Just as an example, in the Northumberland Strait, we had a big system blow through just as we were getting the system mounted in the aircraft, and it blew the whole damn week. We were trying to get our surveys done. And in the Northumberland Strait, a lot of glacial till and red sandstone, so the water was fairly turbid with that wave action. We also surveyed Sable Island, and we got out to about a 16-meter depth, so we were quite pleased with that penetration. About 10 meters on the Atlantic shore up near Port Hawkesbury. Here we got to about 5 meters depth. That's just showing you a previous air photo we have. The red represents the water surface. This is the cliff at the beginning of the cross section, and then this is the actual seabed down below. Here I'm putting in the shaded relief of the terrain model from the Lidar. So you can see out here we're basically into noise, but all of this is real data, and what you're seeing here are basically bedding planes. So what do we do to do a survey? Well, we go out and we establish survey control, and that's what is key in order to get the positional accuracy. And this system should be good to within 15 centimeters vertical. We haven't had a chance to really evaluate that positioning yet, but everything seems to be working out fairly well. This is a satellite image backdrop that shows us the flight lines that were flown for a place called John Bay and Cape John. And what we're going to do is look at out at this cape here. So I pulled up the geology map from 1990. So we can see we have a fold axis coming through here. Lots of outcrop. Things are dipping to the east, and then dipping to the west. There's an inferred fault through this area, and a fair degree of outcrop. Can zoom in a little bit. This is what traditional LiDAR would look like. This is a bare earth model, so we can see obviously it's been glaciated, and this smooth surface is indicative of a glaciated terrain. And we can see we've got some cliffs and some other areas of shallower slope and the wharf here. This is what the bathymetric LiDAR gives us. So all of this information here is submerged. I'm a little disappointed. I thought I was going to get an ah, or a wow, or a holy smokes. I guess in the mapping world, I've been with young people too much, and we were like, whoa, I can't wait to show this stuff. Apparently, it must have been for horses, I'm guessing, because it's fairly old. It's way back in the photos from the 30s. And you can see now it's forest has overgrown that particular section. Anyway, we can see the bedding here, and we can see this major fold taking place. So all kinds of structural detail that weren't available to us. And it'd be pretty tough to get in and survey here. There are a lot of reefs coming off some of these points, so tough to survey this with a boat. Here's that LiDAR again, the traditional LiDAR in colored. And here we can colorize, so now we can infer what the depths are for these different features moving offshore. And, well, what can we see with the photography? Here we can start to infer some of the reefs coming out from this bedrock and a little bit of the strike of the bedding planes, but nowhere near the same detail we can get from the topographic LiDAR. So from a structural mapping point of view, it extends our ability to map those kind of features offshore quite dramatically. We're going to now come in and move to this particular area. Well, I guess first I'll just show this was the coverage we ended up with. So we're now going to look here, and we're going to concentrate on offshore reefs and sediment. Now I'll take you through a quick historic photo, 1936, and what I want you to do is just keep your eye on this sandbar, plus you can see a reef extending out here, and a few times we'll see some big sediment plumes, so we see the main transport movement here. 1939, some of these old photos are fantastic in that they were flown at low tide. Today we don't fly photos at low tide because of the extra cost. The reef, we can start to see a hint maybe of a secondary reef out here that's submerged. We can watch that sandbar, 64. The modern color 97, can't see too much there but a lot of sediment. Fair bit of detail. Now we're into the modern satellite imagery, so we're at the same sort of level of detail as those older photos. Now here's the bathymetric LiDAR. So here we can see the extent of how far we're penetrating out. That cross-section I showed you early on was about here. And you can clearly see the difference between the smooth surface, where we have the sand over top of the bedrock, compared to the actual bedrock surface itself. And we can clearly see these two reef structures extending out much farther than we could ever see in the photos. Along with getting the elevation of the reflected and timing of the signal to get elevation, we also can make an image out of the reflectance. So that's essentially the amplitude of the reflected signal. Okay, remember I showed you that waveform? Darker material will reflect back at a lower amplitude than brighter material. So this gives us the ability to map the seafloor. So let me just toggle back. Keep your eye on the sandbar here, based on its morphology, based on its smooth look. And now we can clearly see, we can map out that sandbar quite distinctively, and this section of sandbar, and to the ecologists and so forth, mapping things like eelgrass is important to monitor the ecosystem health of a bay for aquaculture and things like that. Geologists, not so much maybe, but sand aggregate, mapping the reef and other information may be of value. There's the color image again. And I think I do flip to the geology, for example. Right through here is where we had that syncline axis coming through. And you can see quite clearly, we can look at our strike of our bedding planes here and how they're rotating to the northeast, the reefs, and I don't know. Looking at geophysics, you're always have to put lines on maps to see where perhaps we may have an offset here. Maybe not. I haven't ground truthed any of it for out here. And then we're back to our strike in this fashion. So just see if you agree with those lines. And we can see the strike is quite different on what was mapped. But of course, they only had the luxury of seeing one dimension of a cliff face. They didn't get to see because we have glacial till covering the land part, and of course, did not get to see the strike of the beds offshore. So I hope I can show you there that perhaps this information can be used to further update maps, as I've given talks in the past where we do that on land. Okay, mega ripples. Not that I want you going out and harvesting all the sand here, but it has some potential. Traditional LiDAR, can't see much in the water. Some imagery, we can certainly see that there are sandbars there, large mega ripples. Modern day satellite data, color. With the bathymetric LiDAR, not only can we see the ripples, but we can actually then easily calculate a volume as I demonstrated with the glacial till. The same idea, because we have the height, we can actually map, well, how much volume of sand is there in this particular area. There's the reflectance again, so we can see the sand compared to darker patches of, say, salt marsh, etc. Okay, this takes me to my last slide. So the ability of topo LiDAR is ideal because it penetrates the vegetation canopy. So it's ideal for earth science, way better than air photos because you cannot see through the trees with the aerial photos. So I hope I showed you enough topo LiDAR to appreciate the value to a geoscientist to see through the vegetation canopy. And of course, we can identify bedrock and superficial cover and geohazards to certain degrees as well. The topo bathy LiDAR, it provides a continuous elevation out into the water to a depth where typically we can get in and start doing surveying with multi-beam echo sounding. So here we were out to 15 feet of water, 5 meters. It's pretty safe to get a boat in there. This particular sensor that we own is about 1.5 secchi depth, so you just can't fly at any time. The weather has to be dependent, and the water clarity has to be good. So that's a whole area of research where we're trying to get smarter with the operational side of things, with having wind, weather stations, so forth. The intensity gives us information about the bottom and extracting, and this is an area of active research for aquatic vegetation, but obviously sand deposits, and these are important for things like sediment budgets if you're trying to evaluate erosion and other things like this. And of course, you know, I recall there was talk a while back about the Shubenacadie River mapping or trying to extract the sandbars for heavy minerals in those sandbars. The water would be dirty there, but still we could map the sandbars when they're at low tide. But other areas where perhaps the water's not so dirty, we could get a full three-dimensional map of the river channel for things like looking at extracting heavy mineral concentrates from sandbars and so on. Thank you very much for your time. Is that really only 8 minutes and 50 seconds? That's incredible. Are you taking questions? Are there any questions?
We have time for questions. Dan?
Can you tell me who controls where the surveys are going to get done?
Money.
How many companies are involved?
Yeah, I mean, so we own the sensor, but we don't have any money to just fly it for the heck of it. So we flew probably 9 areas in September, and all of those had external funding. Now, you know, for example, that Cape John area, that was probably about $20,000 to fly and do some of the initial processing. So we are, and we did fly some freshwater lakes around Halifax, Lake Banook with the weed problem they have and so forth. This has potential there. So we're open for business to expand the research, and certainly not charging commercial rates, but you know, we don't own an aircraft, so a big cost is to bring the aircraft forward and do the operation. And you know, at this stage of the game, it's really smart to be out on the water and collect as much ground validation information as possible, or seabed validation as possible. Yeah. We're open anywhere, though.
Yeah. One comment. I wish you hadn't done that. The map was great the way it was.
That's progress. That's it. Thanks again.
Actually, I have a question.
Sure.
Can the survey be piggybacked on some other survey?
Oh, absolutely, and this reduces the cost typically. So if let's say we were going to do a survey up in Cape Breton, and somebody had come up with the money to mobilize the aircraft, so a lot of the cost is what's called mobilization and demobilization. Sure. Getting the aircraft ready, equipped, calibrating the flight, so doing some flights over known areas. And then to piggyback on that is reduces the cost dramatically. So, you know, absolutely. And a lot of times with LIDAR in general, people will say, oh, it's so expensive, I can't, my department can't do it. But the utility of this information is that many different organizations and government especially can make use of it. And a contribution of, say, 5,000 or 10,000 from different departments, all of a sudden now you've got enough pool of money that you can actually do something. But on their own, sometimes not. So a lot of that is to sort of coordinate things is a challenge, but yet that's how things get done.
Could the instruments be added to an aircraft in, you know, in an arrangement like a cluster? If an aircraft was already going to do, let's say, an airborne mag survey, could it be added and do work at the same time?
Yes, as long as there was a hole. We require about a 20-inch hole to have the sensor be able to see down through that. And one thing I didn't mention is that for the bathymetric flight, we're flying at about 400-meter altitude. So fairly low, and it might actually line up with some geophysical surveys. But yeah, I mean, as long as the aircraft has a certain power requirement, it can go in virtually any aircraft. Thanks.